Welcome, everyone. Before we dive into today's session, I just want to explicitly state Tea Kunande, Dr. Nima Madian. That's right, produced by Dr. Nima Madian. I am absolutely thrilled to guide you through this masterclass today. We are going to take a really fascinating journey from the raw, tangible physics of fluids all the way to complex, usable mathematical transfer functions. If you've ever looked at a massive industrial plant and wondered how on earth engineers mathematically tame all those liquids flowing through miles and miles of pipes, you are in exactly the right place. Okay, here is our roadmap for the session. We'll start with the basics of fluid systems, move into resistance and capacitance, and then scale up to tank dynamics. After that, we'll tackle the challenge of nonlinear pumps, and finally, look at linearization and final transfer functions. Let's get right into it. All right, Section 1, Basics of Fluid Systems. So when we're looking at industrial fluid systems, we're dealing with very tangible physical mechanics, right? Imagine a giant valve interacting with heavy fluid flow. But here's the thing. If we actually want to control it, we can't just guess, we can't rely on intuition, we absolutely have to model these physical laws using rigorous math. And honestly, liquid systems are probably the most common variable you'll see in industrial automation. Our main goal here? To derive mathematical models that can predict exactly how high a liquid will get and how fast it's going to flow. And how do we do that? Well, we use physics-based mathematical abstraction, specifically differential equations and Laplace transforms. But before we even think about writing down an equation, we really need to understand the flow itself. Now, you've got laminar flow, which is smooth, has a low Reynolds number, and is beautifully governed by nice linear equations. But it is incredibly rare out in the field. The actual industrial reality, it's turbulent flow. It is chaotic, it dominates those massive industrial pipes, and it's governed by really complex nonlinear equations. This brings us to one of my absolute favorite concepts, the universal language of system dynamics. If you know basic electronics, you already know fluid dynamics. It's true. A physical valve restricting fluid acts exactly like an electrical resistor restricting electrons. And a huge tank storing fluid, it acts exactly like a capacitor storing electrical charge. The physical domains are different, sure, but the mathematical abstractions, they are perfectly identical. Which perfectly brings us to Section 2, Fluid Resistance and Capacitance. Let's kick things off with fluid resistance, which we denote as R. Resistance is created by valves, friction in the pipes, or really any deliberate constrictions in the system. Mathematically, R equals the change in liquid height divided by the change in flow rate. A good way to think about it is it dictates exactly how much physical push, meaning liquid height or pressure, you need to actually force a specific flow rate Q right through that valve. But remember how we said turbulent flow is the industrial default? Yeah, that makes our math a whole lot harder. In a laminar system, resistance is just a nice, straight, linear line. But in a turbulent system, it's a parabola. So when we take the derivative to figure out the resistance at one specific operating point, we actually get 2h over q. So here is the absolutely crucial takeaway, the multiplier effect. For any given liquid height and flow rate, the resistance in a turbulent system is exactly twice the resistance of a laminar system. RT equals 2 times RL. Just let that sink in for a second, because I want you to firmly grasp this mathematical shift. The sheer chaotic nature of turbulent flow literally doubles the system's resistance compared to smooth flow. All right, next up is fluid capacitance, or C. And this all comes down to the good old conservation of mass. Basically, the rate of mass storage in a tank is just the mass coming in minus the mass going out. Simple, right? And when we substitute the physical cross-sectional area of the tank for our capacitance C, we get this beautiful baseline equation. C times the derivative of height with respect to time equals the input flow, Qi, minus the output flow, Qo. Moving right along to Section 3, Single and Interacting Tank Dynamics. Let's bring it all together for a single tank system. Your input flow hits the capacitance to fill up the tank, and your output flow is restricted by that resistance we just talked about. When we combine these equations and apply a Laplace transform, to move over to the frequency domain, we get a perfectly mapped first-order linear system. This right here is the foundational baseline equation for all fluid control. But as you probably guessed, industry almost never uses just one tank. In a non-interacting system, one tank just drains freely into the next one, so they operate totally independently. Easy enough. However, when you have interacting tanks sharing a connected pipe, the height of the second tank physically pushes back against the first one. This creates an emergent physical cross-coupling term in the denominator. Suddenly, our system demands a unified mathematical solution. Now, up until this point, everything we've looked at relies on passive control. We're just letting gravity do its thing and restricting flow with valves. But real-world automation requires active control. We have to actively drive the fluid using multivariable pumps. And let me tell you, this shift from passive restriction to active driving is where things get truly complicated. Which drops us right into Section 4, the challenge of nonlinear pumps. So when we introduce a centrifugal pump, we aren't just letting a valve bleed off pressure anymore. Now the controller adjusts the pump to actively push fluid out of that tank. And here is the core shift you really need to understand. The output flow is no longer just a simple function of liquid height. No way. It is now a highly complex, multivariable function based on both the pressure differentials, P, and the pump's rotational speed, N. And the reality of that multivariable function, it's brutal. Centrifugal pumps create these crazy overlapping parabolas based on pressure differences and flow at various speeds. Basically, they behave highly nonlinearly. But remember, our standard control theory relies entirely on linear Laplace equations. So we completely hit a roadblock here. We literally cannot apply that beautiful, simple linear logic to these messy curves. This leaves us staring down a massive question. چگونه بر این آشوب غیر خطی غلبه کنیم? For our non-Persian speakers tuning in, that translates to, how do we overcome this nonlinear chaos? I mean, how can engineers possibly model a reality that curves and twists in multiple variables when our control computers desperately need straight lines? Well, the answer is in Section 5, Linearization and Final Transfer Functions. Here's the mathematical hack we use to solve this crisis: a Taylor series expansion. What we do is assume the system is operating near a stable, steady equilibrium point. And if we zoom in close enough to that specific point, even a chaotic curve starts to act like a straight line. We basically treat tiny deviations as if they were linear. We introduce two coefficients here: beta, which tells us how flow changes with pressure, and delta, which tells us how flow changes with pump speed. Just like that, we have artificially forced the chaotic curve to become linear. Now we can finally close the loop. Let me walk you through this step by step. First, we know the pressure differential is directly tied to liquid height via a constant. Let's call it alpha. So the change in pressure is alpha times h. Second, we substitute that right back into our brand new linearized pump equation. So now our flow Q is beta times alpha times height plus delta times pump speed. And third, we literally just drop that entire active outflow equation right back into our fundamental tank capacitance equation. Boom. And that leads to an absolute mathematical triumph. By applying the Laplace transform to this new setup, we get two completely distinct responses. The disturbance response defines how the tank height reacts to uncontrolled fluctuations in the fluid coming in, and the control response defines how the tank height predictably reacts when we intentionally change the pump speed. By using these localized linear models, we've successfully taken completely chaotic fluid dynamics and made them fully controllable using standard PID methodologies. We've reached the end of our session today. Through rigorous abstraction from basic resistance all the way to Taylor series expansions, the chaos of fluid dynamics is finally tamed. It's a massive victory for mathematical modeling. But, it leaves you wondering, if we can tame thousands of gallons of turbulent, chaotic fluid with just a few equations, what other physical chaos in our universe can mathematical abstraction conquer? Thank you so much for exploring this with me today. Keep wondering and keep learning.